So welcome everyone. This is a new installment in our LIGO Virgo KAGRA webinar series. The topic is quite different from previous ones. It's still about gravitational waves, but not about the compact binary coalescences like the previous webinar sessions, but about searches for continuous gravitational waves from unknown sources. We have 4 chapters in this webinar, which will each be presented by one of the main speakers. We have Brynmar Heskell, working in Poland, giving the introduction. Rodrigo Tenorio, working in Spain, doing an overview of generic all-sky searches. Ornella Piccini recently moved from Italy to Spain, covering boson cloud searches, and Andrew Miller in Belgium, covering direct dark matter detection with gravitational wave detectors. I'm David Keitel, also from Spain, doing the moderation, and we have 3 additional expert panelists who will help with answering questions during and after the talk. William East in Canada, Andrzej Korlak, Poland, and Cristiano Palomba in Italy. And during the talk, people can please already put questions into the Zoom Q&A function. Don't put them in the general chat. Use that special button, please, and people will get to your questions. And then after the talk, we will also cover some of them directly live. Now we start with Bryn.
The first thing is, of course, to describe the kind of signal we'll be talking about today. So as David said, these are different from the compact binary coalescences that we've already detected with our network of laser interferometers. So in that case, we're talking about a transient signal with a very distinct signature. So it's a chirp that grows in amplitude and frequency until eventually the compact objects merge and the signal is cut off. Well, today we'll be talking about continuous waves, so long-lived quasi-monochromatic signals, so long oscillations with only slowly varying frequency. And we'll see that these are expected to be somewhat weaker than the chirps, but we do have the advantage that they're long-lived, so we can integrate over long stretches of data, and then our signal-to-noise grows as we integrate over longer stretches of data. However, in the real world, things are a bit more complicated. If we go to the next slide, the problem is that we are computationally limited. So especially in the kind of searches we'll be talking about today, which are searches for unknown sources. So if the source is known, we at least know which part of the sky to look for it. We may have measured some parameters from electromagnetic observations, and so we can restrict the portion of parameter space that needs searching. However, if we perform a blind search, then we have to search over the whole sky, or at least some portion of it with an interesting astrophysical population, such as the galactic center. And in that case, it's just computationally unfeasible to search the whole stretch of data at each sky position. And so we have to search shorter segments of data, although you'll hear later about strategies to combine these. And there is a trade-off in sensitivity. Now, it's a trade-off because there are advantages in this, and the main advantage is that we only have to make very minimal assumptions on the signal. So we can actually search for sources that we don't know are there, for sources that are not visible in electromagnetic observations. So what are these sources? If you go to the next slide, one of the main targets for our searches are rotating neutron stars. Now, neutron stars are incredibly compact objects, so we're talking about something with the mass similar to that of the sun, but squeezed down into a 10-kilometer radius. So think taking the sun and squeezing it down until it's about the size of a city, like Warsaw, where I'm sitting now. Now, if you do that, of course, you end up with something that's incredibly dense. And in fact, the interior density of a neutron star exceeds the density of an atomic nucleus. As you can imagine, the physics that we are probing is therefore very different from the physics that we probe in terrestrial laboratories. And in fact, we don't know what the ground state of matter is at these densities, which is why there's that question mark in my little diagram of the neutron star at the very center. And for such a compact object in such strong gravity, we expect the star to be almost a perfect sphere. And now there's an almost there because the outer lower density regions actually are a solid crust that can support deformation, and we also have a strong magnetic field that will deform the star. And so if you end up with a quadrupolar deformation that's swept around by rotation, then this leads to gravitational wave emission. If we go to the next slide, the emission will be at twice the rotation frequency of the star, because this is a quadrupole. And we usually discuss this deformation, which we like to call a mountain, in terms of ellipticity. So the ellipticity is defined formally, as you can see, in terms of the moment of inertia tensor. But if you want to understand what it means, if you think of a constant density ellipsoid for your deformed star, then it's the normalized difference between the semi-major axis A and B of this ellipse. So it's telling you how squeezed the star is. And there are theoretical upper limits on how large the mountain can be before you break the crust. And I've written down a number here, something like 10 to the minus 6. In reality, the limits are very equation of state dependent. And that's actually a good thing for us, because it means that even without a detection, just with upper limits, we can start to exclude some of the more extreme models and probe the interior of the neutron star. And if you want a feeling for what that number means, it means that if you have a neutron star with a 10-kilometer radius, you'd have a mountain that's roughly a centimeter high. And although it would actually be quite hard with that gravity to climb that mountain, it is still pretty small, which means that we expect to be sensitive to sources in our galaxy, essentially. But what's interesting is that if we estimate the number of neutron stars in our galaxy just from supernova, then there's a lot more than we actually see in electromagnetic waves. And in fact, it's been suggested that there may be a population of neutron stars we call gravitars that are spun down entirely by gravitational waves, so lose all their energy to gravitational waves, and therefore are dark to electromagnetic observatories, and we could pick them up with these searches. But it's not only neutron stars we're looking for. If you go to the next slide, please. We are actually searching for astrophysical signatures of dark matter too. So we know that there will be a large fraction of dark matter in the universe. We just don't know what it is. And there are several theoretical suggestions, and these can be probed with our interferometers. So for example, a suggestion is that dark matter is made up of ultralight bosons. And if these form around rotating black holes, then they can scatter off the black hole and extract energy and angular momentum, what's known as superradiance, and form a macroscopic cloud. Then eventually the cloud will dissipate, and it will do so via boson-boson annihilation and the emission of a quasi-monochromatic gravitational wave. Another possibility is that at least a fraction of dark matter is constituted of planetary mass primordial black holes. In fact, you may have heard recently it was even suggested that planet 9 in our solar system is a primordial black hole. And well, if you have these planetary mass primordial black holes in a binary, then the frequency evolution is slow enough that again you have a quasi-monochromatic signal. Then you can also do a little bit more. So if you go to the next slide, you can actually try to use the interferometer as a particle physics experiment. So rather than look for gravitational waves from dark matter, we can try to probe the direct interaction of the dark matter with the interferometer, because as the particles pass through, they can, for example, modify the coupling constants or the mass of the electron, depending on exactly what they are, and this will show up as a monochromatic oscillation that can be detected using continuous wave methods. But in fact, it is not a gravitational wave. We're talking here about really a direct detection. So if we move on to the next slide, it's now time for Rodrigo to start telling you about some of these searches.
Thank you, Bryn. So if we go to the next slide. So the way we like to think about continuous wave signals is always in terms of two sets of parameters, namely the amplitude parameters and the phase evolution parameters. So the first of the sets encodes information regarding source orientation and the nominal gravitational wave amplitude we should be able to detect, whereas the phase evolution parameter encodes any other parameter involved in the source itself, such as the spinning frequency of, for example, the neutron star we'll be looking for, its sky position, or any orbital parameters if such an object is placed in a binary system. Normally, in a search for unknown signals or unknown sources, we deal with the amplitude parameters analytically in such a way that we only look for phase evolution parameters using numerical algorithms. The way we usually do that is by computing the instantaneous frequency of whatever source we're interested in with whatever model we are interested in at the detector frame, and then we accumulate a detection statistic along the frequency evolution track. And namely, during this presentation, we'll be interested in two main models. The first one, which you can see exemplified in the top figure, is that of an isolated neutron star, in which you can see that there's a Doppler modulation of the frequency along year scale due to the movement of the Earth or the Sun, plus another modulation due to the daily motion of the Earth around its own axis, which is reflected in that amplitude modulation that we can see in the figure. And the second model we would be interested in is that of a binary neutron star, in which the Doppler modulation that we have due to the movement of the Earth is combined on top of it with another one due to the presence of a binary companion, which produces an extra Doppler modulation, which you can see in the bottom figure. If we go to the next slide, please. The way we look for this sort of signals is slightly different to the way we deal, for example, with CBC signals, which refer to compact binary coalescences, in the sense that continuous wave signals are expected to last for long periods of time, which is basically months to years. Hence, they are expected to last for a full observing time, for a full observing run. Trying to apply match filtering, which is a standard search or the standard tool to look for signals in data, and we usually refer to it as a full coherence search, isn't feasible in this case because due to the extreme length of the data stream, there's a huge amount of signal templates that we would have to check in order to look for such a signal. Hence, several approaches, normally referred to as semi-coherent searches, were developed. In these searches, the data stream is split into shorter segments, which are match filtered and then combined all together into final detection statistic. These methods have proven to be more sensitive than match filtering, given a fixed computing cost. And incidentally, due to the fact that we are splitting the data stream into smaller segments, we increase the robustness of the search to a model physics, just for example, a neutron star glitches. An example of this can be seen in the right figure of this panel, in which you can see the comparison of the detection statistic for a full coherent search, which is the solid line, versus the semi-coherent search, which is the dotted line. So in this case, we put an artificial signal at the vertical orange line, and we can see that despite the fact that the full coherent search is more sensitive in the sense that we see a more prominent peak compared to the background of the rest of the statistics, the semi-coherent statistics gives us less structure and simplifies the procedure of finding where actually a signal is in order to identify it first and then to a finer parameter estimation. If we go to the next slide, please. During this webinar, we will be particularly dealing with two specific searches. In general, when we talk about the OSK search for continuous wave signals, what we're talking about is a search for a long-lasting quasi-monochromatic signal, which is modulated according to a certain Doppler parameter, depending on the scale position of the signal and whether or not it's in a binary system. If we found nothing, or if nothing is found, we end up estimating the weakest signal we could have detected in terms of the, and we quantify that in terms of the minimum H0 that we could have detected. These upper bounds over H0 are interpreted using different amplitude models. For example, the standard model we've been using so far is interpreting that H0 search in terms of the maximum ellipticity of a nearby neutron star population at a certain distance from the detector, which is a similar parameter to that introduced by Brain in the beginning of this talk. But other models are possible. For example, we could use this sort of upper bounds to limit the maximum fraction of dark matter composed by nearby planetary mass primordial black holes around us. During this webinar, we present two groups of searches. The first one, as I said before, corresponds to search for unknown isolated neutron stars, and it is shown in two publications corresponding to a search during the first half of the O3 run of the LIGO Virgo detectors, and then another one on the full O3 run of all detectors, and another search for unknown neutron stars in binary system using only the data from the first half of the detector. Next slide, please. We started with a search for unknown neutron stars in binary systems. The physical case for this sort of searches is motivated by the fact that a neutron star in a binary system has access to a set of physical mechanisms that could provide a simple way in which a mountain could be constructed or built up in its crust, producing neutrons, emitting continuous gravitational waves as a result of such a deformation with respect to spherical symmetry. And this could be propagated, for example, by accretion from a companion or some similar mechanism. This search, as I said before, was conducted on early O3 advanced LIGO data and used the binary sky-half pipeline. The structure of the search is outlined here. We basically run this pipeline in order to find which candidates could be. In order to find a first set of initial candidates, then those candidates were processed using clustering and V2O algorithms, which would discard anything which seemed inconsistent with an astrophysical signal and more consistent with the instrumental artifact. And any surviving candidate would be followed up using an MTMC algorithm. More specifically, this search looked for a true frequency band in the detector, namely from the 50 to 100 hertz, and then from 100 to 300 hertz, enclosing the so-called bucket of the detector, which is the most sensitive part. And the binary orbital parameters covered during that search are shown in this figure, where the blue dots correspond to the known population of electromagnetic pulsars provided by the ATNF catalog. During this search, we focused on quasi-circular binaries, and we ignored the presence of a spin-down component into the neutron star, in the sense that, provided by the electromagnetic population of neutron stars, the spin-down in such a population was negligible for all intents and purposes of our search. The results are shown in the next slide. So most of the candidates were deemed inconsistent with an astrophysical signal after follow-up, although a small fraction, which turned out to be a little challenging, was consistent with a few instrumental artifacts present in the detector. Specifically, there was one which was consistent with the 60 Hz power line artifact, which is an oscillation detector produced by or coupled to the 60 Hz power line that actually powers it. This table shows a summary of the number of outliers that we were dealing with during the search, as well as how each beta stage dealt with them. And after discarding all the outliers, we estimated sensitivity of our search and then translated it into constraints upon the ellipticity of nearby neutron stars. As you can see in this figure, the ellipticity is currently constrained between 10 to the minus 1 and 10 to the minus 5 for a population located within 1 or 2 kiloparsecs of the detector, depending on the frequency we're considering. And these results start to probe the regime of exotic equation of state, although there's still a gap to cover if we want to go for realistic equations of state with these sort of searches. If we go to the next slide, now we will cover the other set of searches, which are those for continuous wave from isolated neutron stars. In this case, there's a variety of pipelines conducting searches. We have, for example, the power flux pipeline, which covered just the first half of the O3 observation run, and whose primary space is covered in the top figure. And then frequency half, sky half, and time domain statistic covered the search on the full run, on the full O3 run. These four pipelines assume a similar frequency evolution model and are in contrast to the SOAP search, which also runs on the full O3 LIGO data, and which is presented as a model search based on the Viterbi algorithm. The idea of this complementary search is to give an early alert of the presence of of a continuous wave signal in the data. And the idea is that by using the Viterbi algorithm instead of a deterministic model, is able to be more robust to deviations produced by unmodeled physics, such as, for example, glitches or timing noise. If we go to the next slide, the left panel shows the results of such a search in terms of the upper bound on the amplitude in a similar manner to that of the previous search. And these curves follow roughly the shape given by the sensitivity curve of the detector. None of the outliers that we found in the search could be ascribed to any astrophysical origin, meaning we would estimate the sensitivity. And these results, again, are interpreted in terms of the ellipticity of the nearby neutron star population, in this case, giving better constraint in terms of realistic equations of states on the nearby population within 1 kiloparsec. If we go to the next slide, as I said before, the ellipticity is just one of the ways in which we could interpret these upper limits, being the other one, for example, in this case, an upper bound on the merging rate and the abundance of planetary and asteroid mass primordial black holes. The reason for this is that a binary primordial black hole system within this mass range is a low mass system, meaning the in spiral phase of it is it resembles quite a lot a continuous wave with a positive spin-up, meaning the model that would describe such a situation is consistent with that of a continuous wave with a spin-up, which is something we have already looked for. So these results can then be interpreted in terms of what would be the abundance of such a system, or what would be the maximum fraction of the dark matter composed of such a system in our neighborhood. In this case, our results cannot constrain the nearby primordial black hole population, in the sense that this parameter f tilde is greater than 1, and we would expect it to be lower than 1 in order to say a physically meaningful statement. Although we expect future observing trends to be able to keep constraining this population. If we go to the next slide, given these results, now I hand over to Ornella, who will cover more direct searches for dark matter candidates.
Thank you, Rodrigo. So, okay, we can also use interferometers to look for dark matter, both in terms of the gravitational wave emitted by these bodies, or also, as you will hear in the following, as direct detectors for these kind of particles. So first of all, for those who are not very familiar with what is dark matter, so basically the majority of dark matter in our universe is dark. So it means that it doesn't absorb, emit, or scatter of any light of any wavelength. So what can we do to look for it? We can check its gravitational influence. There exists several astrophysical evidence for the existence of dark matter, in particular for why we need it, why we need to this kind of matter. One is, for example, given by the orbital speeds of stars measured from galaxies, in particular our own Milky Way, which cannot be explained with the observed matter, visible matter. So we need dark matter to explain this weird behavior. Same happened for the collision of the bullet cluster, which are two clusters of galaxies, which can be easily explained if we assume that there is some unseen matter, the blue one here you see in the right picture. And there also exist many more clues for this existence. So next slide. Okay, but we don't really know how this dark matter looks. We only know that it constitutes the 85% of the matter in our universe. It barely interacts with ordinary matter. And actually, we don't really know what's the range of masses. And we know that this could be very heavy or very ultralight. So the order of magnitudes of the masses spans like 70 orders of magnitude. So there's not a real clue for this. This could be particles in terms of weakly interactive massive particles, the WIMPs, action or action-like particles, dark photons, stereo neutrinos, and whatever you may think. This can also interact with themselves and with other objects in gravitationally mainly, and can form macroscopic objects. You have heard about primordial black holes. We will talk about boson clouds, but these could also form actual stars like boson stars, and also other compact objects like the matches. So today we will focus on the ultralight dark matter. This is because our detectors are sensitive in the frequency band between 10 and 2 kilohertz, more sensitive in this band. So this is of our interest. It means that we can probe particles in the range 10 to the minus 14, 10 to the minus 11 electron volt. Next slide, please. Okay, so I will focus now on a particular search, which is based on the search for dark matter, but looking at the gravitational waves it can emit, in particular the boson clouds. Next slide. Okay, so just to make you an idea, so you can imagine that you have a very fast rotating body, in our case a black hole, which is spinning very fast. Then you can try to throw on it some small balls. You will see that these balls will scatter off. So this will be bounced back. So this happens when you have a very fast rotating body, and this is what we call a superradiance condition, basically. This is the requirement to have this kind of system, because when this happens, the small balls, in our case, the bosons particles, will extract some energy from this black hole. And so the black hole momentum will decrease and the black hole will slow down. During this interaction, the boson can condensate, clumping around the spinning black hole, and they will occupy the same quantum states with huge occupation number. And this is the reason why we have clouds, so macroscopic objects. This process, this formation process, is maximized efficient, is maximally efficient when the sizes of the particles, by size I mean the quantum wavelength of the particle, is similar or comparable with the size of our black hole. And this process, which is an instability process, typically lasts for days, while when the cloud is formed at this point and the superradiance stop, the clouds start to evaporate. And you have heard from Bryn that this happens mainly via annihilation of two bosons, which dissipate and emit gravitational waves. This in particular has a timescale which is longer than its instability time. So mainly we expect that for most of the observed or most of the existing system of this type, we will for most of the time observe gravitational wave rather than formation process. Next slide. Okay, so in general, given the shape and given the structure and its mathematical structures, so the black hole boson cloud can be comparable to a hydrogen atom. So in particular, we call it the gravitational atom for this reason. And in the same analogy, we can define a fine structure constant, which depends on the two masses involved in this project, which are the black hole mass and the boson mass. The strain amplitude, the gravitational wave amplitude, which is emitted during this depletion, will strongly depend on this alpha fine structure constant, the spin of the black hole, the distance of the source, and okay. So this will scale as in the formula you see there. The gravitational wave frequency emitted by this system would be expected to be twice the field frequency, and strongly depends on the two masses again. We do expect to have a small spin up. This is due to the fact that the boson, that the black hole mass decrease. The boson cloud decreases mass, and so we have this spin up. In general, you can imagine that could be also many more deviations, and the signal could be even more complicated than this, and so this is the reason why I do consider possible deviation, as you can see in this plot on the right. Next slide. Okay, so I will now talk about the recent results that we report in this paper here on sky search for gravitational wave emission from scalar boson clouds around spinning black holes using LIGO O3 data. So as I say, the emitted frequency is dependent on the boson mass that we are considering, and this can be in the advanced LIGO Virgo sensitivity band. Okay, so this search in particular is the first all-sky survey for these persistent quasi-monochromatic signals, and so it's the first time we do this kind of survey. We analyze a frequency range between 20 and 610 hertz. Okay, again, using the latest observing run of advanced LIGO. And also we do consider a small spin-up region near the parameter, in the parameter space. So next slide. Okay, how can we look for this kind of signal? Basically, we typically start from a time series, which is pre-process, clean, and so on. And we can build spectrums using fast Fourier transform, using different length of this fast Fourier transform. This will bring the most important peak in the spectrum can be put together into a map, so a time frequency map, what we call a peak map. And from this peak map, we can do a projection over the frequency axis and look for the most important peaks. So those we are most persistent, basically. Let me say that when we do this process, we consider, so we build the peak map and we do consider the sky position. So because this is an all sky search. And so each of these peak map is corrected according to the expected Doppler modulation. So we repeat this procedure many times. On this set of selected important peaks, we do coincidences between the two detectors, because if there is a real signal, this should be seen in at least two detectors, and we follow up the most significant candidates. Okay, we apply two methods in this search, basically one more tuned for standard monochromatic signals, and the other one which is more robust against deviation. So next slide. Okay, so we didn't have any detection for this kind of sources, and we could place upper limits on the signal strain. You see that we reach lower values actually than the sky search of the order of 10 to the minus 25. And we can use these curves to get some astrophysical implications in terms of exclusion regions in the black hole boson mass plan. And also we can tell how far can we get with this search. So basically how far we can exclude the presence of an emitting system like this given the null results. So next slide. Okay, so concerning exclusion region, we do need first to make some assumption of the black hole population, because this is strongly dependent on this, and we need to suppose the spin, the distance, and the age of the cloud. So you can imagine that a younger cloud will emit for a longer time, so it will emit more gravitational waves, but also that a fastly spinning black hole will emit more. So basically, when we have this higher emission, we are able to constrain a wider region. So in these plots, you can see in the first row an assumption of black hole spin of 0.9, fastly spinning, and we can put our source closer at 1 kiloparsec or farther away at the 15 kiloparsec. You can see in the lower row you have the same, but with the black hole spin 0.5. So you can see that when you have closer sources which are spinning very fast, you are able to probe a wider parameter space. So you can exclude the existence, given the null detection of this kind of signal on a wider parameter space in the black hole mass, boson mass. Okay, next slide. Okay, so you can also check for the astrophysical reach of a given search. Basically, it tells you the maximum distance at which a given black hole boson cloud system, assuming again a certain age, is not emitting a continuous wave. So as a function of the supposed boson mass. So to do so, we can do some simulation of a black hole population using a particular mass distribution. These plots show the one of black hole masses between 5 and 100 solar masses, and assuming a uniform spin distribution between these two numbers. Okay, we can say, okay, the maximum distance corresponding to the distance at which at least 5% of our simulated signals have a strain which is higher than the upper limit. This means that we are starting to detect them, and so we can put some, let's say, maximum distance at which we would have been able to see those systems. So as you can see, we are able to prove farther away regions when the source, the cloud is younger, because as I told you before, it emits for a longer time. And so this is somehow expected. This behavior is somehow expected. Okay, so let me just say that these results are strongly dependent on the ensemble properties of the simulated black hole population. So next slide. Okay, I pass the ball to Andrew, and he will talk about direct detection of dark photons.
Okay, thank you, Arnella. So as Arnella said, I will talk about detection of dark photons. So just to give some context for what I will discuss. So as you've heard in this webinar, as well as most of what you hear from LIGO Virgo and KAGRA, that we look for gravitational waves that come from neutron stars, but gravitational waves that also come from dark matter candidates like boson clouds that we just heard about and primordial black holes. But what I will talk about is not actually a gravitational wave, but it focuses on the direct detection of ultralight dark matter signals via their interactions with gravitational wave detectors in the same mass regime as Ornella just discussed. So these signals are not gravitational waves, but they can cause a similar strain on the detector that resembles a quasi-monochromatic continuous gravitational wave. And so that means that we can use similar search strategies to try to detect them. And in this case, put upper limits on the degree of this interaction of dark matter with our detectors. And so the gravitational detectors are just one way of probing this existence of dark matter directly. There are other experiments like the torsion balance experiment from EAT-WASH and microscope satellite that also answer this question. And we will compare our results to some of these experiments. Moving now to the next slide. So now let me define what ultralight dark matter is for us in this case. and why it gives you a quasi-monochromatic signal in the detector. So we know that we have been able to determine what the dark matter energy density is in the universe, which based on the, and then giving that with the mass of ultralight dark matter particles, this implies a huge number of dark matter particles in any given volume of space. In the equation that you see on the right-hand side of this slide, you can see that this number is order 10 to the 54 for a mass of 10 to the minus 12 EVs per c squared. What this means is that in any given volume of space, that the individual wave functions of each of these dark matter particles overlap, and you can hence model this ultralight dark matter packet as being a superposition of plane waves, and each with its own velocity and each with its own frequency. And this type of dark matter could be generated in the early universe via the misalignment mechanism, and which is a non-thermal generation, and it would form a coherently oscillating field at a quasi-fixed frequency, which essentially means that the frequency is almost a single tone, just like the quasi-monochromatic continuous gravitational waves that we've heard about so far, except now that it has a finite coherence time, which means that the signal is only coherent in a certain amount of time. And then after this, you start to observe frequency deviations, hence the quasi-monochromatic nature of this signal. And physically speaking, we see these deviations they arise from the fact that every particle of this 10 to 50 particles is traveling with a slightly different speed, and which implies a slightly different frequency. And the superposition of these waves at different frequencies gives rise to a small stochastic frequency variation over time that we can observe if we look for longer than a coherence time, which is very easy since we observe for 1 year, and the coherence times are on the order of 10,000, 100,000 seconds. Now, if we move to the next slide. So then the signal itself, the first question we want to ask is, will we see the same signal in both detectors? And it turns out the answer is yes, we will. And this is because the coherence length of the signal, that is the wave, essentially something related to the wavelength of the signal, is extremely large compared to the separation between detectors. Here is a formula on the right-hand side of the slide for the coherence length, which gives you on the order of 1 billion meters or 1 million kilometers. Compare that to the separation of LIGO Hanford and LIGO Livingston, which are on the order of about 3,000 kilometers. And so this is a huge difference. And so we can safely say that there will be correlated signals in both detectors. And this means that we can, again, apply the same kind of methods that we use for continuous gravitational waves to look for quasi-monochromatic signals that exist in both detectors at the same time. And now we'll move it now to the next slide. And so now about what we actually would see in the detector. So we talk about what does the signal actually look like. And so here I provide a plot of that. So if you look on the left-hand side, the left-hand figure on this slide, on the y-axis is the strain. On the x-axis is time, which is 1 day out of the 1 year that we look at. But this is just meant to show you the fine structure of this signal. So you can see that there is a good deal of structure in the time domain. And each of these parts is essentially a coherence time. So when you observe within a coherence time, you do not see much structure in the signal. But when you observe for longer than a coherence time, you can actually by eye look at the green plot and see that there are different pieces of this coherence time that have a little bit different structure. And this is even more visible in the frequency domain, which if you take the Fourier transform of this green curve on the left-hand side, you get a power spectrum as a function of frequency, which is given by the purple curve on the right-hand side. And so here you can even see so first of all, that since you observe for longer than a coherence time, you can resolve the fine structure in the frequency domain. And secondly, that this is a very small frequency variation. This is order 1 millihertz. And this also underscores the idea that this signal is very, very almost at a fixed frequency, is quasi-monochromatic. And so the principle then of the data analysis for these signals, just as in the case of continuous gravitational waves, is that you want to break the data set into small chunks where each chunk has a duration about equal to the coherence time, such that, and this means that this frequency modulation that you see in the purple curve on this slide will be confined to one frequency bin, will exist at one frequency in each of these chunks. And that means that we will not lose any power due to the fact that the signal will not be spread in multiple frequency bins. So all power will be concentrated in one frequency bin, which is what we want to have an optimal search for this type of dark matter signal. And so move now to the next slide, please. And so now I'll talk about the physics of dark photons and so why we expect a strain on the detector from this type of dark matter. So the dark photon is essentially a vector particle that interacts weakly with protons and or neutrons in materials and causes essentially a dark electric force on test masses through this coupling. So essentially, the way that it's formulated is that the dark photon has an associated dark electric field, which then moves the mirrors in a particular way. And so there are two ways that this differential strain happens. The first way is a spatial effect, that there is, since we're talking about a vector particle, there's some element of direction and polarization as to what direction the particles are polarized and coming from. And so there's a spatial effect, a spatial differential strain that occurs because each of the mirrors is located in a different place with respect to this incoming dark matter field. And so this means each mirror moves a bit differently, and therefore you have a differential strain. The second way that you obtain a differential strain is a temporal effect, that it takes the light a finite amount of time in each of the arm cavities to go from the input mirror to the end mirror. And within this amount of time, the mirrors in each of these arms has moved slightly in response to this dark matter field. And thus there's a temporal effect, a temporal contribution to the strain, because light will take a finite amount of time to go back and forth between the mirrors. And so this is seen in this picture here. And so now I'll move to the next slide. We use two methods to search for this type of signal, one based on cross correlation and one based on excess power. So in the cross correlation, we look for we analyze detector data simultaneously with a fixed FFT length, a Fourier transform length. And second, we use the excess power method, which is the same as Ornella discussed previously for the boson cloud signals, that basically allow you to change the FFT length as a function of the boson mass considered. And here's just a picture representing that, where essentially you see this projection onto the frequency axis of a time frequency map that Ornella also discussed. So moving now to the next slide. So the results of this search were a few outliers from each of the methods, and all these outliers were found to be due to some instrumental disturbance. And here we show one example of such an outlier, where an outlier is just a particular frequency that has a high value of a detection statistic. And here you see it in the power spectrum as a function of frequency around a particular outlier which is even by the purple line in this figure. And you can see there's a huge disturbance based on a large comb that has caused an outlier to appear in Livingston and Hanford. And so this means, so we perform these kinds of analyses to veto all of the outliers. Moving now to the next slide. So now the results of this work essentially were upper limits on the degree to which dark photons would couple to protons and neutrons in the mirrors in LIGO and Virgo. And so here you see on the y-axis this coupling strength as a function of frequency. And you can see in red and black/blue the upper limits coming from this search compared to existing experiments, which are the green and purple curves. And so you can see that there's orders of magnitude improvement in these limits. And I remind you that the LIGO, Virgo, and KAGRA were not designed for this purpose, but they can still provide a very stringent upper limits compared to existing experiments that will only improve over time. And so this makes it a very exciting way to probe the existence of dark matter. And so now I will hand it back to Bryn to conclude and to make some connections between what we talked about. Thank you.
Thank you, Andrew. Well, I think really the take-home message here is that we can use continuous wave searches to probe really a lot of very different physics. So from high-density physics in neutron star interiors to dark matter and even direct detections of dark matter. And well, that our searches are now starting to probe a theoretically interesting region. And so stay tuned. The fourth observational run of detectors will begin at the end of this year. And well, indeed, stay tuned for further webinars on continuous wave science. And with that, I think that's it. And I'll pass back to David.
Okay, thanks a lot to all of our speakers. We had 2 questions already that were answered in chat, and I see 2 more now. So maybe we can answer those live. There's one by Peter. Sorry, I will probably not pronounce your last name correctly, Peter Sai or something like that. Would the possible polarization modes be the same for all kinds of CWs as for binary coalescence? So asking about the GR or possible alternative polarization modes. Maybe one of the panelists wants to take this. If there's nobody else, I can give a quick answer that in principle, it depends mostly on the theory of gravity, that in GR you have these 2 standard polarization modes, and beyond GR series you could have additional ones, and indeed you can in principle probe them with continuous waves as well. Of course, you first need a detection, but there are also additional searches that have been done, for example, with known pulsars, which will be covered in an additional webinar looking specifically for beyond GR, things like scalar and tensor, scalar and vector modes, where GR is by default this tensor mode. Then we have one by Lucia Gebauer-Werner on related to the boson clouds, how you model these. Do you have to take into consideration a correlation between the black holes and the clouds? Ornella, do you want to take that? Pass to a panelist.
I think Cristiano wants to answer.
Yeah, so, okay. Yeah, indeed, from the analysis point of view, we are just taking theoretical models for these boson clouds, and what is relevant for us is the basically gravitational wave strain, which is produced by the annihilating bosons as the cloud depletes, over time. And so what is relevant for us from this point of view is mainly how the frequency evolves in time. And as Ornella was saying, the frequency in principle is nearly monochromatic, maybe with a small spin up due to the self-interaction. But indeed, from the analysis point of view, in order to be more robust, we try to not stick too much to the theoretical models, and indeed we try to be able to search also for signals for which, say, some kind of a frequency wandering should happen, even if this is not actually currently predicted by theory. We cannot exclude that something strange or still not taken into account will happen. So we want to try to be as robust as possible. Concerning the correlation between a black hole and the cloud, I'm not sure to understand the question. What we know is that given a boson mass, we need a minimum level of black hole angular momentum in order to have this triggering superradiance effect. So in order to have the formation, the actual formation of the cloud. And then once the cloud is formed and it starts to deplete, then the signal frequency depends mainly on the boson mass, but indeed there is also a correction on the frequency, which depends on both the boson mass and the black hole mass. But I'm not sure if this answered your question indeed, or if you wanted to know something else.
What we'll do is I'll just answer questions, mark questions as answered, but then people please feel free to post follow-up questions when it wasn't quite clear. Next, we have another one that Cristiano can answer by Uri Siaipur. When the source is a transient, e.g. during binary merging, the gravitational wave signal is observed. However, for detecting the first evidence of continuous gravitational wave, it seems more reasonable, although as you say, more difficult to begin with known sources rather than exotic ones, which may depend on many unknowns.
Yeah, indeed, even for known sources, like for instance, known pulsars, which are observed through electromagnetic radiation, we don't know which is the actual amplitude of the emitted signal, because this depends on the amount of deformation of the neutron star, which we don't know. So as it was reminded before, we have some theoretical upper limits, but we don't know the actual degree of deformation of any neutron stars, even of those which are observed through electromagnetic radiation. There is some indication about the possible amount of deformation for some special, let's say, systems like accreting neutron star, and for instance, Scorpius X1 is an example of this class of potential continuous wave sources. And in the case of accreting low mass X-ray binaries like Scorpius X1, you may explain the observed some observed properties of these systems concerning, in particular, the spin frequency of the star, assuming that there is a kind of torque balance among the accretion of matter and the emission of gravitational waves. And in this case, then you may actually have an estimation of the signal amplitude that you may have in the signal. And indeed, we search also for this kind of signals. Unfortunately, our upper limit are still not enough low, or the sensitivity of our searches is still not enough good to completely and to fully test such kind of mechanism. But this is something which will happen in the next runs.
Thanks a lot, Cristiano. Then we have a question that Andrew Miller will answer about the dark photons. Question from Mark Luthi. Would dark photons electric coupling with the neutrons or protons in the LIGO mirrors have a lasting or persistent effect?
Yeah, so I can answer this. So the coupling is basically happening forever. So because the mirrors always sit in this field of dark matter. And so like it will be persistent. It will always be moving the mirrors forever as long as the detectors are on.
Okay, thank you. Then we have one from Elias Messiane that Ornella can answer. Can axions be excited from one level to another by absorbing gravitons?
So in principle, yes. The idea is that this is a second emission channel, but we are not considering this in our searches. First, because this is not the main channel of emission channel. So it emits somehow gravitational waves in this case when it jumps from a second level, but we are not considering it in our models, let's say. It should be also noted that the signal could actually change if we do consider, for example, other effects like self-interaction of the bosons and so on. So yes, but we are not considering it.
Then we have another one here from Adam Kiddle. Is it computationally expensive to take the FFT of segments and produce peak maps over such long periods? I guess that's a question for one of the people who use the peak maps. Cristiano is volunteering to answer.
Okay, yeah, so indeed, peak map production is not extremely computationally heavy. If you want to do it just once. The point is that in the case, for instance, of the boson cloud search, which Ornella described, which is an all sky search, we have to compute the peak map and then apply the Doppler correction for all the peaks which are there. And this, of course, must be repeated millions of times because we have millions of different sky location to cover. And in the end, this becomes rather heavy. So just to give you an idea, the full analysis, which just is not made only of the peak map production, but also by other analysis steps, has been so it took in the end of the order of a few 100,000 core hours to be completed for the full O1 run.
Okay, thank you. I see one more question from George Dishman about a system at 3.11 millihertz. I'm afraid the answer to that is far too low for our sensitivities. That would be for detectors with significantly longer arms, like space-based detectors maybe in the future. And then I'm not quite sure if the amplitude is high enough, but it's outside the LIGO Virgo KAGRA band, unfortunately. Another interesting one from Vladimir Dergachev. Photon shot noise is a major limit to detector sensitivity. What is the shot noise from dark photons? Whether in addition to the signals, they also contribute noise, I guess. Andrew, can you answer that?
Yeah, so I think that like the shot noise from ordinary photons comes from the fact that they're hitting the mirrors, but this is not like these dark photons are not actually hitting the mirrors and moving them. They're coupling to particles in the mirrors. And then this is causing, through this dark electric field that's generated, this is causing a movement of the mirrors. So there's not like a shot noise that's being generated due to the existence of these dark photons. And in fact, the sensitivity of the same noise sources are there. It's just that this dark photon is not contributing to any of them because it's not actually hitting the mirrors and causing this force.
Okay, for some reason I cannot mark the last two as done, but I hope that answered these questions. If there are no further questions, we are almost at the top of the hour and could wrap up here. Then let me thank again all the speakers and panelists and also the audience for taking an interest in this topic. And yeah, we'll have additional analysis ongoing, and we will let you know through the website and social media when there are more webinars scheduled. Thank you.